Okay, and that's all there is to it, I think. So we are now recording, and we're back on, and you can see and hear me.
I see and hear you just fine.
Okay, excellent. So I'll show you the audience because I think we're on. There you go. Doesn't point down very well, but maybe if I put it on that thing.
Earthquake.
Yeah, yeah. Well, you know,
Klingons.
they would fall. Okay, so come back, and so this week we are going to start with a discussion with Dave Unger. I'll get my laptop in a second because I have my questions set up there. And I noticed several of you have posted questions on Piazza, which I forwarded to Dave. We'll get around to those for sure. And hopefully you all had a read this week of the Generation Scavenging paper, and the week before that was the Self-Power of Simplicity paper. And Dave is an author on both of those, the sole author on the Generation Scavenging paper, so authority on the subject. After the Q&A, we'll go back to the regular lectures and we'll cover garbage collection in more detail. So I'm going to talk about mark sweep and copying and generation scavenging in some detail because your exercise this week is going to be to implement some of that stuff. So that said, let me get my laptop and my questions. And actually, there's no reason for me to stand there, really, is there? I could just do that over here if the cable will reach. He said, tugging very gingerly. Just about, maybe. Maybe not. Yeah, let's try that. Okay.
Thanks for dealing with the remote stuff, Mario.
Yeah, it's always exciting to do technology and talks. If anyone sees that sliding to the edge of the table, let me know. Can you see me okay, Dave? And hear?
Yeah.
Yeah, good. Okay. All right. So Dave Unger is my former boss. I worked for him on the Self project and with him on a number of things since then, and has a very long and an illustrious career in programming language design and implementation. The main purpose of this event, of course, was to talk about implementation, but implementation and design are strongly tied, and so we're kind of going to take an interesting trip through many different areas, I suspect, in this hour to try and get some illumination on the subject. So let's start with your early experiences, Dave, and in particular I'm thinking about your interpreter and APL experience when you were an undergrad.
Okay, so just to point out that
But
I
by the
was...
way, we still just see the book.
Yes, I'm about to change it.
Okay, all right.
I just wanted to tell people that the Berkeley work I'm going to get to was done long, long ago in a different century. And the date on the book is 1986. And this sort of will help drive home how many years it's been. There's a transition from that guy to this guy. We were hoping to get a picture of Patterson to show you from back then because he was my advisor. But you'll just have to imagine what Dave looked like many years ago. So let's see, what happened was my high school was one of 3 in the country that had computers in them by some federally funded government program. It had 3 IBM computers in a big room upstairs, and Friday afternoons they ran APL, so my first programming language was APL. And then everything else after that for a long time was a huge disappointment till I hit Smalltalk. But I got to undergraduate school, not Berkeley, but Washington University, St. Louis. The weather was a lot worse. And had to write an interpreter and an assembler and an interpreter for it for the freshman project. Actually, it was a whatever, the first course I placed into. And everyone else was punching cards in PL1, and you can't imagine what that was like. But they were writing 1,000-line programs in an unair-conditioned room with key punches and multi-hour turnaround in an interesting language. But I drove to the APL time-sharing service with a few lines of APL, turned the assembler into APL syntax, and with one operation said, interpret this as APL. Turned in 20 lines of APL, thought I would flunk. When I got an A, my career was warped forever. Languages that were not dynamic were just really, really limiting. And although I find myself working in one today, that set the stage for what was to come later, which was making these languages possible, and then what some might call a perversion of the work, which is what makes Java possible and practical today. But we'll get to that later. Did that answer your first question? Okay, Mario.
Yes, I think that was an excellent answer, and I think it's a great story. I was similarly warped by early experiences, but your story is so much better than mine. I was searching for a picture of Dave Patterson on the web, but I can't find anything more than about 5 years old. Okay, so what was your introduction to Smalltalk? Oh, we lost your audio. It's gone quiet.
Bad. I have a cough button. Can you hear me now?
Yeah.
How many of you are PhD students? Raise your hands. Okay. So, why did I come to Berkeley to get a PhD? I was working at Bell Labs. A project switched away from Unix. I thought, I'll get a PhD. No one will boss me around in my career ever again. Well, I'm here to tell you it doesn't quite work like that. But I came to Berkeley. I was really interested in doing VLSI at the time. It was a coming thing. Went to work for John Osterhout, who's a name you may or may not know. He used to teach there. And there was a guy in the class who was talking about mixed-level simulators. Name was Dan Halbert, another Berkeley PhD student. By the way, the Berkeley PhDs I met there are some of the brightest folks I ever met. And Dan was doing his PhD in Smalltalk at Xerox PARC in Palo Alto, commuting down there in a car he had borrowed from Butler Lampson, which name probably doesn't mean anything to you, but he's sort of a famous guy. And he showed me Smalltalk, and he sat me down in front of, I think it was a Dolphin, which was a big computer, but one of the closest things they had to personal computers. I know we'll get into that later. And all of a sudden, here was a system like APL where what I typed happened right away. It had this new idea at the time, object-oriented programming, which I had heard about from Bjarne Strostrup at Bell Labs as he was doing C++. And I was smitten because I could throw together a stack. All my mistakes gave me feedback right away. I got it running. I really loved the idea of coupling the data and the appropriate behavior. And after that, I had to work in Smalltalk. I had to find some way. Around that time, the X-Tree project was winding down. The RISC project was in full force. The Berkeley RISC, which helped alter the course of computer architecture. And I had this insight that all the same stuff that made C run fast on what would be considered naive compilers today, but we didn't have the cycles for fancy compilers back then, or the memory, would be an even better boon to Smalltalk. And so after the RISC project, I proposed to Dave that we look at RISC for Smalltalk, and that's how my real grad student thesis project was born and there's the title. Answer the question, okay, Mario?
Yeah, great. So tell us about your graduate work.
I'm sorry, about which work?
Your graduate work.
So the first thing that happened was we had a VAX that everybody was using, and of course it got really slow around time to finish one's project. And we had a bitmapped AED terminal for VLSI over a 9600 baud line. And the Smalltalk folks were trying to popularize the language, so they released a tape, and Mario has his own stories about that, with the whole Smalltalk image, and a book with directions on how to implement an interpreter for it, which they ran on a 33 nanosecond Dorado. Did I get that number right?
60.
60, thank you. And that's right. So I built an interpreter. It was really slow. And then I looked at speeding it up. And that's when the generation scavenging work came, and then the SOAR work came a little later. Should I talk about generation scavenging now?
In particular, the sort of the genesis of the idea.
Right. So the standard thing was reference counting. You guys know about reference counting? Raise your hand if you know reference. Okay, you're nodding. Good, thank you.
They all Deutsch, and 2 weeks ago.
Yeah. And Peter talked about his great ideas, and reference counting had real problems because it was slow if you did it really, namely incrementing and decrementing reference counts on every store. It also couldn't collect cycles, which ironically today I'm working for building iOS apps in Swift, and it can't collect cycles either. What a pain. What a real pain. And Peter whispered in my ear, because he'd heard from David Moon, he'd just been at MIT, he was at Berkeley, and he was my mentor in learning this stuff. What if you treat younger objects different from older objects? Well, the MIT way, which I found out later, was to have multiple generations and different and this. And I said, I'm at Berkeley, we do things simple, this is Riskland, two generations. And Dave Patterson said, don't bother looking at this, reference counting is fine. I looked at it anyway. So one lesson is don't listen to your advisor. Okay, everybody got that? Here. And what I did was I did measurements first, trace-driven simulation. I learned that a lot of the young objects died young. And so I built a system that would segregate the young and the old objects and only look at the young objects that were still alive, because looking at the dead ones you'd waste all your time. And then copy the young ones that were still alive from one place to another. And of course, when you're copying, you can compact them. And the first version kept the level of indirection that Peter described 2 years ago, where to go from a reference in an object to another object, you went through a table. And that made it easy to do compaction and worked on a 16-bit Dorado, but 32 bits was all the new rage back then. Can you guys imagine that? And so I said, we'll just use direct 32-bit pointers. And in the process, I bet Peter that I could get a speed up over I think it was the indirect reference count version to the direct version. And I think the number was 1.7. I got him to bet me at dinner that if I couldn't speed it up more than 1.7, I wouldn't get anything, but if I did, he'd buy me a dinner. And being a grad student, free food was the biggest motivator there was. And especially putting one over on Peter, who was certified genius expert and wonderful guy. So I tuned it till it passed 1.7. Got my dinner, some fancy restaurant, which I still envy you all the good restaurants near there, because down here in the South Bay, they're just not. Um, so then I published this paper at a conference, and non-disruptive generation scavenging and non-disruptive high-performance automatic storage reclamation algorithm. And that was a landmark paper because it was the first published account of a generational collection scheme with measurements to back it up and a real implementation. I don't think Moon had published yet. And later when he did publish, his scheme was much more complicated. So that was a pretty big deal. And the problem with it is that there are some objects. This was another lesson I learned when I was at these conferences being real proud of this. These old Lisp guys with gray beards, longer than this one, would come up to me and say, but what are you going to do when stuff lives long enough to get promoted to the old area so you don't have to look at it anymore, but then it dies? It'll take up space. And I said, that never happens. We're cool. But then later on in some follow-up work I did, which if Mario wants I can talk about, it turned out to be a problem and we had to deal with it. So if you rely entirely on generation scavenging, you have this worst case problem. And I coined a name for that problem while I was still at Berkeley. I called it the problem of tenured garbage. So next question.
How did you make the leap from Smalltalk to Self?
Okay. So what happened was, well, let's see, that kind of skips over the SOAR work. Can I go back and...
No, by all means, go back. Go back.
So this project started up with Dave. Dave was a wonderful, wonderful advisor and coach at the time. I don't know what he's like today. And I wrote the sort of all of the implementation of Smalltalk to run on this RISC except for the compiler, which some other buddies of mine wrote. And what I did for the dissertation was eliminated every clever architectural idea one by one and looked at the impact. And only 4 of them won. Register Windows was a big winner. Compilation was a big winner. I believe that tagged integer instructions was a big winner. I could look it up in the book, but it doesn't matter now because some of that's been superseded. So we got prototypes of the chip built. I don't think we ever got Smalltalk running on it, but the simulations show that this 330 nanosecond, if I remember the numbers right, 33,000 transistor chip could keep up with the 60 nanosecond ECL Dorado. And that was really cool. That got me my PhD. I went and taught at Stanford. What?
Boo, hiss.
I used to go into my classes with Go Bears signs. And then they titled their projects with acronyms like Beat Cal. It was a lot of fun. And while at Stanford, I was trying to figure out what research to do. If you go into academia, you're going to face this problem. What do you do for research? Coming from Berkeley, I was really fortunate that didn't know how lucky I was. I had grant money that didn't have a lot of strings attached, including a Presidential Young Investigator and a Micro Award. Dave and John Hennessy, who was the head of the lab at Stanford, really did a great job in supporting their young faculty. And that gave me the freedom to do research in whatever direction I wanted. And if you get that freedom, don't waste it. I didn't. Find something really impossible that motivates you and do it. Is it okay that I'm giving you all this personal advice along with the technical? Okay, okay, I see some heads nodding. Um, so here's the deal. I'm at Stanford. I'm teaching programming languages and architecture. The PhD students there are really great, almost as good as Berkeley PhD students. And I'm consulting at Xerox PARC because that's the land of small talk. I meet a guy, Randy Smith, who has this system called the alternate reality kit. And I don't think I have time to show you that, but the point was that small talk, with its combination of object-oriented metaphor, rapid turnaround, decent performance on the Dorado, let people create things you couldn't create in any other context. And when I look back, this is really the motivation for the work I did that changed the world, but not necessarily in the ways I hoped it would. Because the things people were doing there was astounding. Dan Halbert was doing, I think, a programming by demonstration dissertation. Randy did this physics simulation to teach children physics. And the laws of physics were these tangible things that moved and were animated, which was amazing back then. Randy did the first drop shadows on the screen when you picked something up and moved it. Before, just outlines would move when you dragged the thing on the screen. You have to remember, this is 1985, 86. So, in particular, he had this load balancing simulation, because load balancing was new and distributed stuff was sort of new. And each computer was like a star, and the jobs were like planets orbiting the stars. And a planet, if it was too crowded, it would sort of make the journey to another star and orbit it, modeling the time it took to migrate a process across the network. And he had these forces worked out where they were attracted to stars and repelled by the other planets, and you could move these things around. And I, being a wise guy, said, well, what if you glued a star to the back of a planet? You know, what would happen? Would the system go nuts? And in any other world, he would have had to stop, open up a text editor, type something in, deal with compile errors, and then restart the whole thing. But of course, we never have to do that today, right? We never work in an environment where we're editing text and looking at files and restarting our programs to change them. But in the alternate reality kit, implemented on top of Smalltalk, he just grabs a star, drags it to the top of a planet, and pulls up a menu that says glue. And the thing gets glued to it. He didn't even have to go back into the Smalltalk level. And this was the genius of Randy Smith. And so I knew I wanted to work with this guy because he saw things in a different way. And then when the Smalltalk group said, you know, tell us what the next version of Smalltalk should be, he and I started this series of meetings, which was really fun. At lunch, Peter Deutsch said to me, Smalltalk has 7 different kinds of variable access. You know, they're still basically in Java today. Local, class, instance, pool, which corresponds to sort of packages, and some others that don't matter. Why does it have so many different kinds? And Henry Lieberman had published a paper on prototypes, but I didn't like his formulation. You might want to go back and read it. And so Randy and I, we also didn't like, Randy's a theoretical physicist by training, and most object-oriented languages have classes. And in many of them, classes are not objects. In the ones where classes are objects, there's a conceptual infinite number of classes in any program. Because a thing has a class, that class needs a class, that class needs a class, that class needs a class. And then they do various cheats to do them. Smalltalk had objects, classes, metaclasses, and then a strange loop. Nobody ever understood metaclasses. So how do you get rid of meta classes? You get rid of classes. If you don't have classes, you don't have meta classes. And in the real world, you know, here is a thing, there is no class. It just tells you everything about itself. So the 2 points in self were, things are self-describing. You don't need a class. You don't need any other thing. The whole point of classes, every time you see a class in an object-oriented language, think implementation detail that the designers weren't good enough to cover up. And JavaScript even has them too, only they don't call them that. Brendan Eich, many years later, read a self paper and kind of got it wrong. But the other key idea in self was unification of state and behavior. And again, in the real world, you know, you really can't tell if this is a thing or if this is just the behavior of a bunch of stuff behaving in a way to seem like a thing. And so why not unify? Everything is a message. If you don't say where the message is going to, it's sent to self. Self being the core of object-orientedness, that there's this one thing that determines the context of the computation, and it's so important we never mention it. That's the key idea. Procedural computation, foo always means foo. Square root always means square root. Display always means display. Once you go object-oriented, there's something that is self at the time that you're not seeing, and when you see foo or square root, it means send a message to self and interpret this in the context of that self. And occasionally you send a message to some other thing. So we came up with this beautiful language. The Smalltalk group, I don't know what they did, but they didn't do the next version of Smalltalk. Randy went to England. I'm looking around for a research project, and I'm thinking, this language looks impossible to make it go fast. You know, everything that was a load is now a virtual message send, a virtual function call, which was the killer in Smalltalk. The function call and return frequency was so much higher than anything else because the way you made things different was to override a function. And if you're going to override functions, then your functions get really small so you can override them very frequently. That's how you get variation. So the key, I mean, the reason why register windows were even better for Smalltalk was we had this high call frequency because we had lousy compilers, because we had slow machines with not much memory. So that's how the self project at Stanford was born. And I had some pretty darn good graduate students. And there's nothing like the feeling of power you get as a young faculty member with freedom to not attend too many committee meetings, a relatively light teaching load, which still seemed real burdensome at the time, and 3 or 4 students who can do, you know, 5 impossible things at breakfast and only fall asleep once every 3 days. That's amazing. I haven't, you know, really had that. Well, the self project, which we'll get to. So that's how self got started. And does that, am I ready for the next question at this point?
Yes, yes. So tell us about the vision for the system and the consequences on the implementation.
Yeah. Okay. So I'm going to tell you something right now. I don't know if it'll make any sense. I hope you obey it. Do not ever build a compiler. Do not ever build a language implementation. What you want to build is like the Small World Disneyland ride or the Pirates of the Caribbean or something like that. What you want to build is an alternate reality that fools somebody into thinking that something is real that is not real. Operating systems courses don't explain this to you, but this is what operating systems are all about. How many people think files are real? Well, they're not. Good for you. They're just an illusion. There's no reality to a file. There's a lot of work being done to make you think, well, what is necessary to convince you that it's real when it's not? Several things. One is you never see the intermediate stages. You never see the way the file is organized on the disk. Another is it never gets corrupted. It never behaves in a way you can't explain from the model of files and directories. Another is no time elapses. When you create a file or remove a file or move a file, it just happens. It doesn't take any time. Similarly, if you forget about the damage done to the field by compiler experts, you realize that what you want is you want your program, you want the computer to fool you into thinking that it's executing your program just as you wrote it, word by word. You don't want it to take any time between the time you write the program or change the program and it starts changing its behavior. You don't want to ever see any error that is not explainable in terms of the source code for the program itself. You want it to run fast, but when you start debugging it, you want everything to look like there's no optimization going on. You never want to see anything like a jar file. That completely destroys the illusion. So the vision was, oh, and you don't want to see browsers. You don't want to see tools. Tools are a stupid idea that made sense in the 70s when we had PDP-11s and the programmer's workbench. I was at Bell Labs when they coined the term, although not in that particular organization. A tool is a thing you build because you only have 16K of memory to fit a particular function into. What you want to see are the pieces of your program that matter to you for the task at hand, not a window, not a thing where you have to navigate through a hierarchy and another thing and another thing. You want to see this piece of your program, that piece of your program. And that was the vision for self. So I had a few students, and together we came up with the ideas. You see, if you're doing a Disneyland ride, the code that's compiled and run, inspired by what you heard about 2 weeks ago, doesn't have to bear any correspondence to the source code, as long as you can never see it as a user. So we can compile multiple versions. If we have an access that you're calling as a user like a virtual function, but you know in some context it's an access, we can compile code to do the access. I call that customization. So when it's inherited by this refinement, which is our equivalent of a subclass, we could compile it one way. What's inherited by this other thing, we could compile it another way. And we followed these ideas along, and I'll get to the details in a minute. But the version for the user interface was things of your program, not tools. And we even brought in cartoon animation techniques, which we were some of the first to do, and won awards for papers from 10 to 23 years later for all of this stuff.
Yeah,
so go ahead, Mario.
Speak some more to the cartoon animation, and I'll wiggle a box for you.
Okay, and tell me when you're wiggling it.
Okay.
So the point was, I had a young son. I had a fancy VCR. That was a thing that existed long ago to watch recorded video before there were iPads and stuff. And it had a good jog shuttle control, so we could freeze frame through. And the people who did, let's see, how many folks have seen Disney's Pinocchio? That's like the big classic. How many folks have seen Bugs Bunny? How many folks have seen Popeye? Okay, the guys who did that, and it was a combination of men and women doing different stages of the process, they knew how to cheat. They knew how to convince you that a drawing, a flat drawing going at usually 12 frames a second, was a living, breathing thing with feelings. And they used all kinds of techniques. There's a classic book, Disney Animation, The Illusion of Life. The folks who did Bugs Bunny cheated more than the Disney people. and yet obtained spectacular results. The folks who did Popeye cheated even more, but that's another story. And I got fascinated by these cheats because at the time, when anything moved on a computer screen, it moved slowly, like this. Because if they moved it quickly, it just looked like more than one thing moving. And I knew that we could do tricks like moving it in a single. When the Roadrunner runs off the screen, in one frame he goes from here to here with a streak, a dust or smoke or whatever. And I knew that we could steal those techniques. And one of the techniques was what's called follow through. When the Roadrunner stops, he wiggles a little bit. And one of the things I wanted to do with our self-user interface was when you connected two things and the arrow went, it wiggled when it hit, and it wiggled just right. So it wasn't in your face, but it was noticeable. It let you see what was happening without using as much of your conscious brain. Do you have it up on the screen?
I do. I've got the UI1 running, and I can summon an object, if you like, from the lobby.
Sure. Summon an object, drag an object around quickly on the screen so they can see the streaks. And no one had done this. No one had applied the lessons from Pinocchio and Popeye and Roadrunner to making things legible on the screen. Today it's everywhere. You know, Apple did it first, I think. Apple did it early and really well. Web designers do it all the time. But we had machines with no graphics hardware. We had an 8-bit frame buffer with a color map. And we did stupid color map tricks. We didn't even have X in the first version. The color map was the screen. We did stupid color map tricks on early 68,000 Sun machines to get this to go at 30 frames a second. And the story, go ahead.
Yeah, no, I'm wiggling and clicking. It's all moving around, but I'll let you keep talking.
So the point is, I came into Sun after the project had moved because at some point, Bill Joy and Emil Sarpa at Sun Labs said, come work for Sun, leave Stanford, you won't have to teach, we'll match your salary, we'll match your consulting, all you have to do is work on self. And at the time it seemed like great. They hired my grad students, they hired Randy to co-lead the project. It was fantastic. Little did I know that in a few years they'd cancel the project, but that's another story. If you ever have a teaching career where you're choosing between teaching and industry, come talk to me. I'll tell you my experience. It was not unmixed. On one hand, I got to bring Mario to this country, along with Randy, and some other guys like Lars Bach, who learned stuff in our project and went on to do interesting things. And on the other hand, when it was over, it was over. So I came into this office because you couldn't work at home, because you couldn't have the computers there because they were still expensive and big. And I wanted to make the box wiggle. And I had to use trial and error to get the program right to make it wiggle just so. But the self system gave me this combination of tremendous fluidity in my program, being able to make changes really quickly and try them out, and fantastic performance for the time of how fast the program ran. And it was the implementation techniques that made that possible, that combination. And it was I'm not going to build a compiler. I'm building a Disneyland ride that forced us to make the compilation pauses invisible and the debugging so easy that one could keep doing it at 4 or 5 in the morning after one had lost most of one's ability. So the implementation stuff was in service of being able to do things like this, where you didn't know exactly what it had to be. It was called exploratory programming at the time. And the language was so simple, you didn't trip over what flavor of this do I use, because there was only one flavor of anything, which is called the Allen Kay principle. And all those things came together to build a system that enhanced one's productivity as one got stupider and stupider.
So just to really emphasize this, when I pop up a menu here, if you look, you'll see it doesn't just appear, it grows in place. And when it disappears, it shrinks back in. Everybody's completely used to that now. That's absolutely standard, I think, on most systems. But this was the first system to do that. Before that, if I went to a system and I clicked on a location for a menu, the menu just appeared all in one go. So it just sort of came from nowhere. And when I let go, it disappeared. And so nothing had the feel of sort of tangible reality to it. And as you can see, you know, it's really hard to tell on a fast machine. You have to kind of slow the video down. But it is drawing blurred images when I wiggle this thing around to make it look like there's really only one thing there. It's not just a high frame rate that's populating this. That would look quite different.
Go ahead, Mario.
Go ahead.
We didn't know this would work. We didn't know that not ever changing a pixel abruptly would be good. We just thought it might be because of the way the human visual system works. And we didn't know that using the advice in the Disney book that everything starts slow, speeds up, and slows down at the end would make something that was easier to understand when you were tired. We just thought, well, let's try it out. And we didn't know how much to slow it down at the end. And we didn't know how much it should wiggle. But we had a system that let us play and gave us good performance and easy debugging. And we didn't have to worry about things like jar file paths. Go ahead, Mario.
Sure. So I think that's actually a great moment to maybe take some questions, because most of my remaining questions are sort of more what you might call philosophical in nature. We've been going, 40 minutes or so. So at this point, I would like to open it to any questions from the audience that are kind of immediate reactions to what you've just seen and heard. We'll get back to the ones you sent in via email after that. But does anyone have any immediate responses? Patrick?
So both self and small talk are closer to the languages nowadays than APL. Do you ever miss like the way of thinking in APL?
That's a great question. And the answer is, I sort of ignored functional programming for many years because of the mess of the type systems. But now I've been doing Swift for a year and a half. And I can write APL in Swift, except that the type system will complain about a bunch of errors and slow me way down. But it's a lot of fun. I'm back to that. I used to do some of that in Self too, with blocks and collection methods. Like in Smalltalk, they're called inject, select, reject. But Swift is even more with filter and map and flat map. So I'm back to it, and that's kind of the fun part. But I miss the fluidity of APL and the immediacy of the interpreter when I work in Swift. And the type errors at this stage in the lifetime of its tooling are not well expressed. They're getting better all the time, but they have a fur piece to go. If in APL you get an operation wrong on an array, you can execute it stage by stage and watch. If the type system barfs, you have to kind of go back and rewrite your program with a lot of extra type declarations to see where what it thought the type was not what you expected the type to be. And that's painful. And there are people working on that. They need to make the operations of that stuff much more tangible and accountable. And I don't know what the state is in pure functional languages. Maybe it's better, the state of the tooling. But it's not there yet. Does that answer your question?
I see the points being made about like self and there's been a handful of other things like APL, the immediacy of it, the interaction. But then I see these sorts of things and they always make sense for like,
you know, little simulations or whatever, and then I try and imagine writing something significant in it, something large, like a database or like, I don't know, a genomics sort of analysis thing. And suddenly, I can't imagine how I could write something that would take a million lines of C. I can't imagine how I would write something in a language like this.
So there were large things written in Self and Smalltalk and other languages. They became smaller when written in this versus other languages. By the way, Sue Graham, my programming languages teacher, will tell you that when I got to Berkeley, I thought C was the best language in the world. So I've sort of been there. But the answer is you break things down into small pieces and you test. And you test pieces. And then you put the pieces together and you make bigger tests, and pretty soon you've got a big system that all works. And is that an answer that satisfies you, or can I help more?
Yeah, I think so. You have to actually, I think yeah. It's the sort of thing that comes with experience. Actually
Well,
seeing it,
yeah, experience can be transformative there. Mario, you want to say something?
No, I was just going to call for more questions if we were done with that.
Yeah, well, I'll just say that no matter what you're doing, any language, or any job, you break any piece of engineering, you just break things down into small steps where the steps make sense, and then you test it, and then when you find out your breakdown is wrong, you break it down differently. So that's the best answer I can give. It works for me anyway.
We have a question up in the front.
Yeah, maybe just kind of like a follow-up to the last question. But I mean, I know with large kind of dynamic language projects, you end up with like a lot of tests that are basically just replicating a type system. So like guarantees some type is going to be the same. I know with a static language, you just hit compile and like it runs the compiler's way faster than like the 50,000 tests or whatever you have on your dynamic language once it starts getting really large. So I don't know if you have any like comments on that.
Yeah, the great thing about this is that there are no bugs in compiled and statically typed languages that compile. And that's why we see no problems with security on the internet, or Windows never crashes and all of that stuff. So there you go. I mean, absolutely.
Well, I'm just talking like compiling faster than running the test that checks the types. Like,
I'm sorry, I didn't hear that.
like if you have a lot of tests that are basically just replicating type checks, those tend to run a lot slower than if you were to just run a compiler in like a Java or C or C++ compiler even.
That's interesting. Has that been your experience? I don't know if it's been mine. My experience was that the bugs that type systems found were easy to find and fix with or without type systems, and easy to test quickly. But the real bugs that always plagued me were ones that were really hard to find and fix, especially in most cases because I just didn't think of the problem right. And type systems never helped me with that, ever. The tough bugs were ones where a new situation would come up and the thing wouldn't do what I wanted it to do. And then I write a test to do that, so I knew I didn't get that bug again. But that's just my experience, and it all depends on the problem domain as well. You know, an algorithmic bug or a synchronization bug in your collector, and things run well most of the time and fail sometimes, or a bug in your compiler that I had in Self in some grad student code, and I won't name the student, but he wasn't a Berkeley grad student. He came from another continent or from MIT. I'm not sure who wrote that code, where the register allocator and the stack location allocator had similar names, and he used one when he should have used the other, and when you ran a particular benchmark for an hour and it re-optimized 3 times out of 5, it would crash. That was a bad bug. But I had to maintain their code after they left, and those are the ones that scare me. And
So those question at the
Yeah.
back. Loud.
Small talk on a risk goes back to your hardware experience. Small talk on a risk is based on risk. And risk, the risk philosophy was kind of a rejection of hardware support programming. And so I was wondering if you could comment on how you and Patterson add stuff. And if you thought any of it was
Sure. So the philosophy was find simple things to support the common case, because the sense in which it was a rejection was that at the time there was the Dorado and the VAX. Both had huge instruction sets. The Dorado was user microprogrammable, and they were optimizing memory and spending a lot of hardware to do this. But we looked at the thing, for example, the Smalltalk bytecode set's a zero instruction stack based instruction set. The VAX had like a CRC instruction in it.
Polynomial was my favorite.
Yeah. So the RISC thing had looked at C and said that the big cost is subroutine calls and the data movement that you need to get the right things in the register for the next subroutine. And we can fix that with register windows, which was a great idea at the time because no one had the horsepower to do a lot of interprocedural optimization, which is what happened a teeny bit later at Stanford with the MIPS architecture. And Smalltalk had, go ahead. Oh, I thought, go ahead, Mario.
No, there was, you picked up some experience. Keep going.
Sorry. So Smalltalk had the problem even worse, and there was this problem of these, the fact that these were dynamically dispatched. Well, Alan and Peter cracked the dynamic dispatch problem with inline caching for SOAR, and then it got adopted for Spark. I devised the one-cycle call instruction by putting the immediate call target address in the 30 bits of the call instruction with a 2-bit opcode. We could do calls and jumps in one cycle, and because of the register windows, the register motion was very fast too. We had 8 windows of 8 registers apiece on chip, and we could get really good performance. So that was key. And then we did a lot of other things to support hardware, like age tags to support scavenging and the arithmetic bits. But the 2 big things I remember were compilation from stack byte codes to 3-address register code and Windows. So it's not that you don't do hardware support. That philosophy at the time, it was that you do it very carefully and much more less than what people were doing at the time. Go ahead.
From here? Yes?
Oh, the comment was an earlier question, but the point was that you're right. Type systems are only catch 7 bucks, and will never catch a logical bug. So that was the only point I had. And there won't be relevant about this
Okay.
conversation.
Okay. So, tell us a little bit about what you thought of as the main innovations in implementation itself, and in particular, I'm curious as to what you think the trajectory of the work would have been had it continued to be funded and supported.
So we started with a compiler, the second or third rev of the compiler was this thing that used control flow graphs and did inlining and type inference all at the same go. And it was really clever, but it had some problems. It did things like if it saw A plus B, it would compile a common case and an uncommon case, And if it saw something that it thought it might inline because the size of the called routine looked small compared to some arbitrary threshold, it would inline it. And it had several. One was we never got the runtime performance we wanted. Another was we had these compilation pauses that made the system unpleasant to use. And the third one was when we succeeded in getting the Stanford integer benchmarks to run well, the slightest change to a program would cause them to run poorly. And but it was brilliant work, and it was the basis for the next PhD. That was sort of the first PhD's worth of compiler work. Sometimes it takes more than one brilliant PhD. Around that time, we came up with the idea of the polymorphic inline cache, which I think was at least partly mine, maybe Orr's. And the idea was, what do you do when you have everyone know what a monomorphic inline cache is? No.
A standard inline cache as Lecture6 described.
Okay, so you've got your inline cache, but now your program is ping-ponging between two different kinds of objects. And maybe the routine it's calling is simple in either case, but the problem is every time it comes through the cache misses, you fall back to the lookup, you pay the price to flush the cache and put a different thing in it. Well, that's going to be slow. One of my favorite professors at Berkeley, William Kahn, Velvel Kahn, I think he's emeritus now, used to talk about the devil. You know, what if the devil comes to you with a program that causes this cache to oscillate and miss? Well, I think this part of it was mine. I said, well, that's easy. We'll just compile a stub. We'll find rooms somewhere else so we don't have to move the code. We'll branch to it. And we'll have basically two inline caches in succession. Test if it's this thing, go here. If it's that thing, go there. So it's really more of a type case. And once you've got two, why not have n? Well, if the devil comes with three, okay, we'll make another one with a thing and a thing and a thing. And that was pretty cool. And then I think it might have been Urs who came up with the brilliant idea, let's put counters in these things. Well, now after it runs for a while, we can go back and look at the counts and see what's really happening. And then we can recompile, because remember, I had this customization idea that we were already using. We can go back and replace this code with something that just knows the patterns. And even cooler, I might have contributed to this, what if it's in a loop? Well, what you want to do is not recompile the thing in the loop body, you know, in a thing that's called by a thing that's called by a thing that's called. You want to recompile the whole loop and inline the whole thing, so you get a nice tight loop. So that was the idea behind adaptive optimization. And to get rid of the compile pauses, we use a really quick and dumb compiler for the first round. Later, Lars and Urs replaced that with an interpreter for later VMs. Put a quick and dumb compiler in, put in counters, watch the counters, figure out what the hotspots are, and that term was coined, I think, by David Staudemeyer. We didn't use the term back then. Recompile, use the type feedback information to optimize. And then I insisted that if you hit an error or a breakpoint, that the system automatically reproduce de-optimized code and take these stack frames that had been there for the optimized inline stuff and map them back to de-optimized stack frames. And I coined the term dynamic de-optimization because I like the irony of the term. And what that let you do is preserve the illusion that we're not doing any inlining. You know, if you change a routine that we've inlined while you're executing the thing that's about to call the inlined routine, we can patch the thing you're executing invalidate it in some fashion or another, and then make it so that the next time you logically call that inlined routine, even though it was inlined, you don't see the obsolete inline version. You see the version you changed. Because we're not building compilers, we're building Disneyland rides. It's really important to me that we did that. Because otherwise, at 4 in the morning, you could get really confused about what was going on. So, we did all this trickery with the adaptive optimization, and we got performance, and we got not much brittleness in the performance, and we got no compilation pauses. And we did various other trickeries, and we got something that was amazing, and we published papers with titles like Making Pure Object-Oriented Languages Practical, Combining Responsiveness with Performance. And this was great, a lot of publications for everybody. Does that answer that question? Oh, the next thing, right?
Yeah, where would it have gone? Where were you headed?
I always wanted to get Urs to stay and redo everything in self itself and do a metacircular version, which I got to do later, till I was sort of fired for doing it at Sun Labs, but that's another story. Because if the language is good and the compiler is good, you want to write it in itself and get all the benefits of that. And you know, if the Swift compiler were written in Swift, it probably wouldn't core dump so much. But of course, it's really hard to convince people to let you do that because it's a lot of work and the payoff is not immediately visible at all. So that would have been the next thing. And when I finally got around to doing that on a smaller scale with Adam Spitz, we had a virtual machine for self, in self, where we could do the same kind of fix and continue on the virtual machine, which was really cool. Your virtual machine has a bug, you're in your nice self environment, you change it, you hit continue, and the bug fix is there. You don't have to restart or anything. You know, that's the way it ought to be. Why do you ever have to recompile and restart? Or clean recompile and restart? You know.
Yes, question.
Regarding this sort of notion of fix and continue, so it seems to me that if it's broken, there could be all sorts of state that is essentially garbage that you fix and continue. How do you pick up like where you're going?
That's a great question, and there are a couple of answers. One answer is, it's nice to be able to restart the world when you really need to or when you're worried about it. It's nice to be able to continue a lot, really nice when you're not. But it's also nice to be able to look at the world, see if it's broken, and fix it up. So one of the tools we had for our garbage collector was a thing that looked at the whole heap and checked all the invariants of the heap. You know, made sure we didn't have any dangling pointers in the heap, etc. And to debug the collector, we'd run that before and after every collection. And so once you have those tools, a lot of the times you can just fix and continue because you know you can run a verify and keep going. And that preserves the state and preserves your mental state and doesn't tax your short-term memory and all of those good things.
Perhaps we should go to the emailed in questions, which I think hopefully you have copies of them, and then we'll wrap up. Yeah?
Sure.
So do you have those in front of you, or do you want me to read them to you?
I do not. I could search, or you could just read them to me.
I've got them. Okay, so first question from Jack. The paper briefly discusses the problem of prematurely tenuring an object that later dies and wastes space in the old area. While the paper makes it clear that this is rare, it also suggests some strategies for dealing with this issue, such as an adaptive tenuring policy. Did you end up pursuing any of these ideas or others to address the premature tenuring problem, and if so, how effective were they?
So the answer is yes and very. But what happened was I got hired to consult while I was still at Stanford at Park Place to help Frank Jackson do the garbage collector for Park Place Smalltalk, which was the rewrite of Peter's Smalltalk that was going to be in C, going to be multi-platform, going to be a commercial product that would make Smalltalk a big success in the world. And things were pretty good, except one customer had this screensaver that drew cute curves on the screen. And the problem was the geometry objects that it used to draw the curves lived just long enough to get tenured and then die when it cleared the screen and drew the next set of curves. So here we had this case that caused the scavenger to not work well. So what did we do? We implemented a thing that Alan and or Peter, I forget which one, sort of poo-pooed 2 weeks ago, but I think it was a tour de force and did things that were used later on. Frank coined the term pig in the python, what I called tenured garbage. Basically, the thing lives long enough, the collector swallows it into the old generation, and then there's this big lump of junk. And we combined the scavenger with a concurrent mark and sweep collector with hooks to the user to say when to give it time or how incremental, and it automatically ran in think time as well. So with that hybrid system, we had a common pattern called hybrid vigor. You take two things, each of which is weak, you put them together, and you get something that combines the strengths of both and mitigates the weakness of each. The scavenger gave fast, imperceptible pauses for the high bandwidth garbage, and the incremental mark sweep collector that I think could also run concurrently was slower, but it could reclaim stuff that the scavenger missed. Was that all the question, or did I forget part of it?
No, I think you got it.
And there's a paper on that called Demographic Mediated High Performance Collection, Argle Bargle the Flim Flam, something like that. I put the word demographic in there and feedback mediated.
I'll make sure to get the full reference. Okay, next question. This is from Johan. What aspects of MMU CPU design are most important for garbage collection? Are there some things that you wish today's common hardware platform did differently?
Yeah, I want memory to be back one cycle away from the CPU, or 2 cycles at worst. I could do...
I know a way of solving that for you, Dave.
I can make the relative overhead of collection really low if you can just give me that. Actually, Mario did a project called Mushroom, where he, garbage collection, in my opinion, is not the problem, it's compaction. That's the problem. A fellow named John L. White did a paper at Xerox PARC in the late 70s, early 80s, proposing for Lisp systems that they never do garbage collection. They just let memory increase and let virtual memory fill up. And in a way, he was prescient, because with the size of disks today, why bother? The problem is that when stuff dies, you get fragmentation, that the hardware to do the address mapping tends to be thought of as expensive, and so they do it on 4K or megabyte granularities now. And so when stuff dies, your page frames get filled up with, a live object, a bunch of garbage, a live object, a bunch of garbage. And you end up using real memory inefficiently, or cache memory if it's on a fat granularity. And what Mario showed, and I hope you present to them this sometime, was how to let the cache address mapping hardware, which you need anyway, do the work of mapping these tiny objects, which are typically 10, 8, 16 words long, because people think in terms of 7 plus or minus 2, so they design objects that way. And let that do the relocation from virtual memory to physical. And Mario, you can address this much better than I. But that's what I think you really need to do efficient compaction, as well as moving objects between processors. And you need software control of the cache, fill and flush, or other things that I think you did later. But that would be my answer to that question. The problem is all these Verstunkene levels of the memory hierarchy and the fact that they don't give you fine enough granularity and relocation and enough software control.
Thanks.
Yeah.
I didn't pay him for the hands up. The next lunch is on me. Second question from Johan. Some people were surprised to see Go, a system programming language, adopt garbage collection. Were you, or did you view this as a natural progression?
So, as I understand it, the goals for Go were to build a language that a large number of people would use to build a large corpus of programs at Google. And garbage collection has pros and cons. The big pro is that you get safe pointers, and the errors in your program are explainable in terms of the language manual. If you're writing a C program and you clobber the return pointer on the stack, which I have done in Fortran, and I've probably done it in C as well, the way your program behaves is something you could never understand from reading the C language reference manual. It'll just do something really wacky. And when you look at the effect, it's very hard to backtrace to the cause. But when you don't have wild pointers and you have pointer safety, every error you make is explainable in terms of that language model. And that's huge. The disadvantage of garbage collection is it's going to impact performance. It's more complicated to do an implementation. Your implementation may have bugs, and those will give you errors that are unexplainable in terms of the language reference manual too. So it's a trade-off, but I think that for most programming tasks, the garbage collection side tends to win big. And I suspect they adopted it for Go because they must have felt it was a big win. And I can see it when you have a huge number of programmers and you're debugging other people's code and you have large programs. It seems like it might be a big win, and performance is so good these days that they probably were willing to take the hit.
Last question. Colin, the ratio of time to execute one instruction, time to access main memory, and time to access the backing store has changed dramatically since this paper was written. That's in reference to the generation scavenging paper. Do you think generation scavenging is still applicable, perhaps changing constants, or do you think a different approach entirely would be better suited to the current landscape of latencies?
Well, I would say yes and no. The reason why I think generation scavenging works is because people like to make aggregates of things to hold temporary results and then throw them away. And in fact, I think the move towards immutable things in variations of quasi-functional programming only exaggerates that. So if you're going to have not worry about ownership, and if you're going to make a bunch of things and throw them away, you're probably going to have a lot of young things dying young, what I call infant mortality. If you have infant mortality, you want a strategy that doesn't spend time dealing with the dead babies. If you have a strategy that does that, you've got something like generation scavenging. Now, if you've got a system with levels of the hierarchy, you'd want it to be cache aware somehow. So that's a big, huge wrinkle on it. And what you'd love is Mario-style hardware that gives you some software control. But that's what I would do if I were doing this today. But again, I would urge you not to, well, I'm getting ahead of myself. I'll stop. I'll save this for the next bit. Go ahead, Mario.
So that, I was going to wrap it up at this point. We've been going about 90 minutes. It sounded like you had something else you wanted to add.
Yeah, I was going to say, don't build virtual machines. Don't do it unless it's in service of some larger vision, because it's a lot of work. It's painful. It's not easy, and the world doesn't need one more virtual machine doing some stupid language, and I won't name any names. I admire what the Swift people are doing because they have a larger vision. I wish the tooling was more like a Disneyland ride, but maybe they'll get there. I think they probably will. We had this vision for self, and looking back, it was about helping people be more creative, letting them work at 4 in the morning, letting them get rapid things back. But whatever the vision is, have one and then do the work. Don't, people will pay you to make some prosaic thing go faster, but where's the fun in that? And you can always publish papers about some new. When I was at Berkeley, the big benchmark was TROF, because people did all their dissertations in TROF, and I watched someone, it might have been Robert Henry, I don't think so, get his PhD dissertation from Sue Graham with a new register allocation algorithm for the C compiler that gave a 3% improvement in TROF. And that was the PhD. And you can always get published results and recognition and fame and fortune from making something that people already do go a little bit faster. And it will save money in the world and save trees and all of that stuff. But what's the point? Do something that's magic. Have the vision. Okay, that wraps up what I wanted to say about that.
Thanks, Dave.
Sure.
Are there any final questions from the audience? I think we should thank Dave for giving generously of his time. And I'll hang it up, and thank you very much. And,
Oh, it's been a pleasure, and boy, the feeling of power you get as a lecturer with students in the room hanging on your every word it creates the academic occupational disease of thinking that you know stuff that you don't know.
Thanks, Dave.
You're welcome. Take
I'll
care.
try and remember that this afternoon.
Okay.
See ya.